how sensors are becoming smart and how sensors are used in the present Internet of Things. Then we'll talk about the sensor trends briefly. This is all just a brief thing we'll have. Then the actual thing what I would like to deliver is how we can design the sensors, either MEMS or NEMS sensors, and what are the softwares used for modeling these things. I will not go into much details because the time is limited. Then we'll talk about one simple application of a microcantilever design and its applications. Typically, most of my scholars are working on these things. And I'll also try to demonstrate you some modeling through PPT only, because if I connect the software, it will ask a more bandwidth. So I cannot connect that software. Up to some extent, I'll show you the softwares. So starting off, what are the IoT sensor devices? If you see, every sensor that can be connected to the internet, every sensor or the sensing device that can be connected to the internet can be called a IoT sensor device. Now, when we say connected to the internet, obviously it needs or it should have some functions. As you can see here listed, the functions are it needs power supply, needs a power supply. And to interface this thing to the internet, or to interface the sensors to the internet, we need a microcontroller unit, AMCU, which is a supporting function which is trying to build the relation between the sensors and the internet. So there are different thousands of different sensors we come to see in our day-to-day life. Obviously, the sensor is the costliest part in most of the systems. That is where the cost of the systems keeps on varying, which will cover when we go to the next slides. And of course, there are hundreds of different communication methods to interact with these sensors. Not only what do you say, the microcontroller is unit or microprocessor unit is playing an interface, but you can interact in different ways. You can have you have wired means, wireless means, you are having Bluetooth, Wi-Fi, or you are having the RF transmission. So there are different means of communicating with these sensors. Then there are hundreds of power supply options, obviously, because depending on the type of application, depending on the location of the application or the place where it has to be used, we have to select a particular type of power supply. And obviously, the difficulties that arise is the diversity. That is, the same sensor which is cannot be used for the same application in other locations, because obviously there are plenty of environmental effects that play a role, and that surely has to be considered while designing a sensor. So most of the sensors which will be designed are very much affected by the environmental conditions, and they will obviously suffer from some limitations with respect to those environmental conditions. And obviously, power utilization, low power, they should be utilizing very much low power. So we when we talk about MEMS sensors or the micro sensors, obviously the total system is a combination of ASIC and sensor, and ASIC is nothing but a application specific integrated circuit. So obviously the power utilization is playing a very important role over there. So what is the power a sensor is using, what is the power the circuit is using. So obviously, if you take the example of our mobile itself, we have multiple sensors in our mobile. So simply, if you see, you have a accelerometer, you can switch off the accelerometer. You have an option of switching off that, or you have touch sensors. Of course, there's a touch sensor available with mobile, or if you see, a touch sensor is laptops are also available nowadays. Even you can switch off that touch option for laptops if you have an external keyboard. So this helps in saving the power utilization by these sensors. Similarly, the other aspects, that is the low cost, also makes a IoT sensor difficult to implement, because as I told you, sensors are the costliest part of any system. A simple example I would like to quote over here. If you see a car, like a simple nano car, which is also carrying four people, which also has four tires, and not more than four people can travel in a nano car. Similarly, if you take a BMW car, even that also carries four people, that also has four tires. But where the major difference arises? Is it the space, it is the tires, or it is the design? So if you see here, the number of sensors that are used in a nano car are much lesser than the number of sensors that are used in a BMW car. A BMW car uses more than 1,000 sensors, whereas a nano car uses less than 10 sensors. Obviously, the number of sensors that are used will obviously change the cost of the device. And also the, what do you say, the specifications of the sensors, or what do you call in terms of measurement, the characteristics of the sensors that are built up when making a sensor obviously play a role in the selectivity and sensitivity of the sensors. So here, if you see in this diagram, I have shown you number of sensors which are used in our day-to-day applications. You can see an accelerometer, a gyroscope, a light sensor. I use a marker. Uh, right. So if you see here, a accelerometer, a gyroscope, a light sensor, image sensor, these are all almost nowadays everything is are being incorporated into mobiles. So what are sensors used for? This is what primarily we should be knowing. So as I was telling you, we are giving our world a digital nervous system. The human body is what is being trying to be mimicked into the whole world. Today we are talking about artificial intelligence. We are talking about machine learning, and we are talking about putting all these things into Internet of Things. So where does this artificial intelligence comes from? It comes from human intelligence. So obviously the intelligence what the humans are having are now being replicated into machines. So that is what is the artificial intelligence we are talking about. And the ability of learning the things what humans are having is being replicated into the machines. That is what is the machine learning we are talking about. So obviously the sensing part is also something which our humans are having and are being replicated into the machines, and we are trying to enhance their sensitivities, and we are trying to improve their capabilities very much similar to human sensors. So if you take a simple example of eyes, a human eye. So a camera is replicating a human eye, any camera. So if you see, a camera can adjust or focus the imaging area. A camera can scan the imaging area, but it is not having as much sensitivity as a human eye. Similarly, the if you take the ears, the audibility, the audible devices are also not to that range. So here, people are always working on enhancing the sensing systems. Even though we have already some existing sensors, but still people are working on how can we enhance this sensing system. So obviously, we want to do their number of sensing elements that are shown on the screen. You can view them. So people are always working on how we can improvise these sensing things, how we can get a much more better sensitivity or a much more better selectivity, reproducibility. So these are all the characteristics of any sensing system. So how sensors are used today? How sensors are used today? So if we see, sensors are used in every location. Might be we feel sometimes, so this here also sensors are used. That is, sometimes we feel, if you see, we have just listed few things. Building automation, that is, we want to monitor the structural health monitoring. This semester we were doing one project on structural health monitoring, where we incorporated some sensors into the building, and we want to measure the structural health of our building. That is, because every building has some aging effect, or even the bridges have some aging effect. So obviously, to monitor their health, obviously we need to have some sensors which are continuously looking after the vibration effect, or what do you say, the loading effects, and they give information through wireless means or wired means. Then health care or life science is one major area that plenty of problems are there, where people can work on sensors, or we have plenty of sensors being used. If you see pressure, your blood pressure or temperature, body temperature measurement, chemical analysis, that is the blood analytics, or we are having light sensors where we have X-rays, plenty of other things. Then we have biosensors, or we have, and so there are plenty of sensor applications, especially in the healthcare and the life science applications. Then we have consumer and home automation systems. If you see the health and life science applications, it plays a very important role. The sensitivity that is expected in the sensors used in this healthcare and life sciences is very high, and we'll be talking about these things later on with some applications also. Then we have the consumer and home automation applications, where the sensitivity will not be a much issue, even though a sensor failure is not a big issue. Like whatever the mobiles we are using, or the sensors that are there in the mobile, say accelerometer or gyroscope, even though it is not of much sensitivity, it doesn't make any difference, because it is only for general purpose utilization, and that doesn't damage to the much, or create a damage to a large extent. Then we have the transportation. Obviously, the transportation also is having number of sensors. If you see the vehicles, what we are using today, the most of the modern vehicles are having a intelligent fuel injection system. What is this intelligent fuel injection system? We are having a sensor which can sense the loading effects on the vehicle, and with respect to the loading effects, it will be giving the amount of, or it will be injecting the amount of fuel into the vehicle or the combustion system. Then you have industries. Obviously, industries use a huge number of sensors. Generally, we are not talking about industrial sensors. We are mostly talking about the micro sensors, which can be used at the common usage. Then obviously environmental sensors, safety, security and public safety, and retail and logistics. So there is every place where we have heard, we have visited, or we have seen, or we are experienced, every place we have sensors being used. Then what drives sensors progress? What drives the sensors progress? So here, coming to our MEMS sensors, the micro electromechanical systems. So we'll have a detailed discussion about MEMS. But basically, if you see why these sensors are becoming popular, the MEMS sensors are becoming popular, because they are digitally friendly. That is, they can be easily in terms. They are versatile, precise, small, and above all, they are very much low power consuming. So obviously, consumer electronics created some economies to scale to reduce the cost. Typically, of course, a MEM sensor, making of a MEM sensor is costly, but with playing with the economics, what the MBA people do, we can surely scale down the cost. So IoT benefits from the MEM sensors. So if you see the smart sensor development in consumer electronics, the reference is missing. You can view it's from here. It's there. The MEMS journal. It's from the MEMS journal. So you can see as the Apple iPhone introduced with three sensors in 2007. Earlier in 2005, actually Samsung introduced with accelerometer, but later on in 2007. iPhone came with three sensors. You can see ambient light sensor, the proximity ambient light sensor. Then we had the magnetometer in iPhone 3. iPhone 4 had a gyroscope. Then we had high performance microphones in iPhone 5, and so on. You see the number of sensors have been increasing. And if you realize, as the number of sensors are increasing, the cost of these mobiles has also been increasing. Today, the iPhone is much costlier, which is having number of sensors. Okay, it is having a good number of health monitoring sensors also. That's why the number of the cost of the mobile has also gone up. Even though the processor has enhanced, even though the RAM, the memory, and everything has enhanced, but above all, the cost increase is mainly due to the number of sensors that are used in these phones, the smartphones. So if you see the sensor trends, it's only for a view to show that every area has sensors being used. Still bending sensors today. People are talking about wearable sensors. That is, we can wear the sensors onto our body, and they will do the activity. Of course, we are already having them in the market. The smart watches, if you put on your wrist, it will be telling how much time you are sitting, how much time you are standing, how much time you are walking. So there are number of such sensors which are monitoring your health conditions, and you are having photodiodes or the light sensors, then the IR sensors can be utilized from this screen. So, going to our major topic, today's topic of discussion, MEMS and NEMS sensors. So, what is this MEMS and NEMS sensors, or how do you differentiate this MEMS and NEMS? So, before going to this thing, I would like to take a small poll from you people. It is okay for you. One second. Many of you are aware of this. I have to do the screen sharing. Share. Right. It should. Right. So everyone can view the poll. Just try to give your answer. There are good number of people who are aware of MEMS. So we'll have some polling in between as we go further also, such that and you can also view the result parallelly as it is running on the screen. As the people are polling, you can see how many are saying yes and how many are saying no. Out of 83, 33 have given the answers. Right. So let us continue because it's almost like 40-60 ratio. Most of them saying no, and plenty of them are saying yes also. Right. So, shall we close the poll? There are only 37 responses out of 84 participants, 83 participants. See, nothing wrong in polling. It's only to know the status of the participants such that I can go in much detail, or I can push off few things. Good. Right then. So we'll stop. Even though I have given 5 minutes of time, yeah, 50% we have reached. 50% of them have answered. 32 out of 84. Right. Okay. We'll stop. So very good. Uh, is it visible? Okay. You can answer.
It's visible, sir.
Right. Fine. Okay. We'll start. Say the characteristics, everything are expected to be the same. Otherwise, the dimensions of the device for a MEMS is that any one of the dimensions should be in the, and for NEMS, any one of the dimensions should be in the nanometer. So we can integrate both mechanical and electronic components on the same chip at the micro and nanoscale. So here, primarily, where the concept of this MEMS came from. Let us have a brief history of where the concept of MEMS came from, and then we'll go further. So if you see, the semiconductor industry has grown mostly from the early 1900s, and we see that the electronics has been miniaturized, micro-sized, and even nano-sized. We are having plenty of developments in the electronics part, where from very years from long years back itself, we are able to use the ICs or the integrated technology, the very large scale integration technology for miniaturizing the electronic circuits. So, but people, when they started using this miniaturized electronic circuits with the large scale sensors or the large size sensors, it was looking like a cartoon, a big head with a small body, or a small or a big body with a small head. So something, it was something not apt. Then people thought, why can't we reduce the size of the sensors also, and why can't we use the same IC technology what is being used for developing the small scale circuits or your integrated circuits for developing sensors also. So that is where the concept of MEMS came from. And if you see, most of the technologies that are used for fabricating or building the MEMS sensors are very much similar to the fabrication process of a VLSS circuit, a very large scale integrated circuit. But the only difference that arises it, a VLSS circuit, most of the time the process is same. You don't have any change in the process. The process is fixed. The only thing is that the structure of the circuit changes, or what do you say, the number of devices on the circuit change. But when it comes to a MEMS device fabrication, the process varies from device to device. That is where the actual complication arises, and that's why even though the cost of the semiconductor circuits has been going down, but the cost of the MEMS sensors is not able to be brought down because of the complexity in the fabrication process. We cannot have a standard process for every device, or we cannot have a standard process for every sensor. So obviously that is where the major difference arises. And coming to the field of MEMS sensors, even when I started way back in 2009 research into MEMS field, I used to think, what is this MEMS? Who works in this thing? But it is purely a very much interdisciplinary field. When I was working at IIC Bangalore, I used to see mechanical people, civil people, biology people. They used to work in this MEMS field. They used to develop sensors related to their field, and it is very much purely an interdisciplinary field where everyone and anyone can work into this field and develop sensors related to their field or related to their applications. So, what are the enabling technologies for this? As I was discussing, it is having both a top-down approach and a bottom-up approach. We are having microsystem technology, where as I told you, the dimensions typically are in between 1 micrometer to 1 millimeter, or we have the nanotechnology, that is the NEM sensors, where the dimensions are between zero point 0.1 nanometer to zero point 0.1 micrometer. So obviously, if one of the dimensions of this device is having the range in the nanometer range, we call it a NEM sensor, or if one of the dimensions is having in the micrometer range, we can call it a MEMS sensor. So the dimensions are not just like that selected, but with respect to the application, with respect to the sensitivity, with respect to the characteristics that are expected from the sensor, we try to select the dimension and design that particular sensor. So the same thing, what is MEMS, as we were talking about the micro electromechanical systems, we can see the number of MEMS products available. We are having micro sensors as well as micro actuators. So the total system, as we are talking about system, should have sensing as well as actuation system. That is to do the sensing part as well as to take the action and give the output. So as you can see, it is having acoustic waves, biomedical, or these are the applications where we can find the microsensor. Similarly, we are having number of end control elements or the final control elements, which are the micro actuators. And very popular applications, what we see in our day-to-day life, we see in the inkjet printers, we see the read-write heads, or we have the micro device components, the palm tops, the mini robots, toys. There are plenty of applications where we find these MEMS applications. So if you see, what is the typical size of a MEMS device? If you see, this is an ant head. uh, it's very much blown up, or it's a image taken under a microscope, where you can see the head of an ant, and the ant is holding a micro gear. There's a gear that is holding, the ant is holding in its hand. So that is the typical dimensions of a MEMS device. That is, a gear was built in this dimension, the micrometer range. So it is normally these devices cannot be used with our normal naked eye. What are the advantages of MEMS? As I told you, it is incorporated with the IC technology, so you can have integrate multiple functions and the precision, improved performance. You can undergo batch fabrication. So obviously, when the batch fabrication facility is there, it will reduce the manufacturing cost and time. And above all, miniaturization. That is, with miniaturization, it is having portability, ruggedness, low power consumption, easily and massively deployed, easily maintained and replaced. It will harm to environment. So if you see the MEMS as a micro sensor, as I was telling, it is a total unit like this. A example of a pressure sensor is shown here. You are having the micro sensing element, you are having the transaction unit. That is obviously transducer plays a very important role over here. That is converting the measuring variable to an electrical parameter. Primarily, we are all using electrical devices. So obviously, converting this sensing parameter into a electrical parameter. Similarly, you can see a MEMS micro actuator, a motor, as you are saying, it is giving the output from the transaction unit. It is giving the output. When you see the sensing element, it is taking the input and giving it to the transaction unit, whereas the micro actuator is taking from the transaction unit and giving the output. Something like this thing. You can see a image over here: starter, rotor, okay, or the transmission gears and everything. So if you see the components of a micro system, it is a combination of both sensor and actuator, and in between you have the signal transduction and processing unit. This thing makes the whole micro system. So if you want to put it into an intelligent system or a intelligent micro system, you can see you're having the MEMS part or the sensing part, the input, you have the controller, you have the processor, the signal processor, where you do the processing, the measurements, comparator, and overall you give the measurements and action. So this makes the total intelligent micro system what we are talking about. So if you see here, the multidiscipline, how this is multidiscipline, or the applications where you can find what an electrical engineer does, or what a mechanical engineer can do, or what a material engineer can do. Chemical engineer, electrical means, when we mean to say electrical, it talks about all the electrical, electronics, communication, instrumentation, all the people. And what a chemical or instrument engineer can do in the MEMS field. So coming to the applications, we'll talk briefly about few applications, not all the applications, because the time will not be sufficient and there are a huge number of applications. And we'll directly go into how we can design the sensors, which is our main topic of discussion. Right. So if you see here, the applications. Am I audible? Somebody gave a message that I'm not audible.
Yes, sir.
Yes, yes,
Right.
yes.
Fine. Fine.
Recently audible.
Right. Fine. So, getting to the applications, we find a good number of commercial applications in automotive, biomedical, process control, communication, okay, inkjet, all these things. So I'll just list out few applications. This is a car. You can see number of sensors in a car. It can measure the tire pressure. It can measure if there's a, what do you say, we have the airbag system nowadays where with some crash, immediately the airbag opens, or you have the fuel injection system. Is a fuel injecting cell. Okay, what you can see, it is much smaller than this coil, so which can sense how much fuel it has to be injecting. Then we have the air quality monitoring, air quality in the car. Then we have what do you say, the pressure monitoring systems in the car, temperature monitoring systems in the car. So there are good number of sensors that are used in a car, the micro sensors. Then we have the pressure sensors belt, which is used in the jet planes, as you can see. This is a series of pressure sensors, or we call it an array of sensors that is uh, together to measure the pressure, air pressure on the wings of a flight. Then we have the optical or a gas sensor, which you can see. This is a gas sensor, which is and this is a image. It's a image of the gas sensor, very much similar to an IC. Then we have smart tongue for food packaging. We all know that there are good number of food industries that are available. We have the lace being generated or the pickles being generated, and we cannot. Every industry needs a quality assessment process at the end of the product developed. So obviously, if you go into the food industry, how is the quality of a food assessed? We cannot make one person sit at the end of the making the product and taste every product whatever is being produced. So obviously we need some sensing devices which can sense the quality of the product. So there is one sensor, a smart tongue, which is generated for food packaging. It can sense the quality of the food that is being generated. Similarly, we have electronic nose for sensing the order. This has plenty of applications. Even all the gas sensors, what we talk about, are very much similar to an electronic nose where they can sense the volatile compounds. So this is the major thing what plenty of them might have been waiting for. So I have shooted fastly into this topic such that I don't bore the people with the theoretical. So let us come to our major part of this. Before I start this thing, again, I would like to take a poll. How many of you are aware of this thing? Give me 2 minutes. Right. So I have another question. Beautiful. Right. My question is, are you aware of console software? I just want to know how many of them are aware of console software. There are a good number of people who don't know console software. Nice. So obviously, they should be interesting for them. Almost 33% of them, 34% of them are unaware of console software. And 8%, only 8% of them are aware of console software. Good. But still, the polling rate is very less. We are having only around 38 people being polled out of 86 participants. What we are having. Anyhow, that's not a issue. Let us start with the softwares. So if you see, uh, the MEMS design, that is the sensors design, not primarily because it is a physical structure what we are talking about. So obviously we need to make the 3D models for the sensors and do the thing. So there are good number of softwares available. I have listed only few, but there are good number of softwares available for designing these tools. So very and I've listed only the popular ones. IntelliSuite is one such software, and we have it in our lab under our project. Then there is a console software, which we have a very old version, a 4.2 version, the licensed version. But most of the times, people try to get the pirated versions of console. And then there is a Convener, which is also a very good tool used for design of MEMS devices. Or not, when we say MEMS, it's not only MEMS, but it also implicates NEMS also. Then we have ANSYS. Actually, I'll show you at the end. You just try to remind me because I have not put it in my slide. But we have a free version of ANSYS available, which can also be used for designing the MEMS devices. But you should be having a student ID because typically it is free for the students, or student ID, or you should have your college ID. With respect to the institutional ID only, they will give you the freeware. You can go into the ANSYS website and log in with your college ID, and it will be a licensed version, and you can use it freely for 30 days. And every 30 days, you have to renewal. Renewal is also a free process. After 30 days, again, they will you have to log in, re-log in, and generate a new license. So that is one thing I'll show you through Explorer only at the end if time permits. Then I'll close this poll. Right. Anyhow, so good number of people are not aware of console. So anyhow, I'm not going to simulate all the things because simulation will take plenty of time, or I'll not design things. I have prepared the slides for of each and every step how the design process can be done in console, which will be very much useful for you. I hope uh, the organizers will share the slides with you people, and these slides will surely be useful for you people when you use this, right?
Yes, sir.
Is this gone, the polling thing, or is it visible on your screens? Anyone can answer. The polling one.
Answer.
Is it visible?
Yes, sir.
Okay. Now? Now is it
Not
visible?
visible. Not visible.
The polling link,
Yes, yes.
or is it gone?
Yeah. Yes, sir.
Polling link is not there. Now
Not there.
only
Okay.
screen is visible. Screen is
Okay.
visible.
Right. Thank you. So we'll start off with the design in console. I thought of demonstrating a gas sensor, but we'll start with a simple cantilever only, because if I directly go into the gas sensor, it will be very much complicated for beginners with console. So typically we have, as soon as you open the console shortcut that is available on the desktop, you will have a window like this. A window will appear like this with three options: a model wizard, a blank model, or a application wizard. So typically we can go with the model wizard, or we can also select a blank model, but we are not going for application wizard. So once you are having good knowledge, you want to build an application straight away which you want to publish, or you can put it onto web servers, you can use the application wizard. Otherwise you can start off with a model wizard. And you have, as I told you, the devices that we are going to design are all three-dimensional devices, but of course we can also design them in that two-dimensional mode and convert them into three-dimensional mode. But preferably, to make it easier, we select the 3D mode only, the three-dimensional mode, that is you can see on the screen. Even there are 1D options because there will be few parameters which will be more signals in the space, which are 1D signals. So such kind of things can also be interfaced or linked up with this software for analysis. That's why even the 1D option is also well. But as of now, for MEM sensors, we will be using the 3D mode or the three-dimensional mode. Then you can see the physics has to be selected, as the software is COMSOL multi-physics, because every sensor surely has some or the other physics involved. So obviously the software is also called COMSOL multi-physics, and it's a very popular software and user friendly and especially student friendly software. It is very much popular in the student community. So you can see the different physics that are available for designing or selecting to work with our sensor, whatever we are trying to design to work with our sensor. So what kind of physics we want to select. So we can see we are having the AC/DC, that is for electrical parameters, or we are having the acoustic to handle the audio parameters, or you are having the chemical species transport. If you are having some chemical analysis or chemistry to be involved into that, or the electrochemistry and the electrochemical sensors, we can use it for. Similarly, fluid flow, heat transfer, optics, plasma, radio frequency, semiconductors. This is what our concern is. So typically, we work with semiconductors and the structural mechanics. So we select a structural mechanic, and under that again you have a number of parameters under the structural mechanics. You have what you want to design, a beam, membrane, shell, or what kind of analysis you want to do. You want to do the joule heating. This is what we use for our gas sensors also, the joule heating. Or you want to get a piezo-resistive response. If you see a cantilever, again there are different types of cantilevers, optical cantilever, piezo-resistive cantilever, piezoelectric cantilever. So there are different cantilevers. So with respect to the type of application, we select the mechanics. So what kind of structural mechanics we want to select. So here we have selected solid mechanics, as you can see, and it shows what are the physics variables. Then once we have selected solid mechanics is nothing but what is the physics we want to add to our device. As of now, we did not design the device. We are only doing the parameter selection. So now under the study, you see, we want to do a study of the device. So what kind of study you want to do on the device? You can do a eigen frequency study, or you want to build a frequency domain study. That is how you want to what do you say, how the frequency of the system is varying. If you take a cantilever itself, a cantilever is having a natural frequency. Any body has a natural frequency. So obviously it will be vibrating in the or resonating in the natural frequency mode. Now when it is loaded, when any body is loaded or when the cantilever is loaded, obviously its frequency changes, and this change in the frequency is what you called it as frequency shift. So typically the application where we find this the resonant frequency shift is in measurement of mass. That is, I think I have that slides, even I'll show you at the later stage, where we can see that the shift in the frequency is occurring, and this shift in the frequency is directly proportional to the mass of the body. So why we want to measure the mass of the body? So if you see the virus, today we are all sitting in the home and listening this webinar because of a major virus called COVID-19 virus or the coronavirus. So we can find or what do you say, determine such kind of viruses using this principle, because this is a very sensitive parameter, and you can get a accuracy to 0.001% and a very high sensitivity to measure such viruses. Even we have slides at the later stage. I will show you these things. Then, so here we are not selecting stationary or frequency or eigen frequency domains. We have selected a stationary domain. This is the simplest application that we can select to start off to learn console software or even IntelliSuite or CoInterware. So we select a stationary mode where we want to only measure the deflection property. So once you select that and say okay, Once you select that or double click that and you say done over here, or you are double clicking this, it will obviously directly go into this page. So here you can see you are having whatever we have added. We have added the solid mechanics. We didn't fix the parameters for our device, but we have added solid mechanics in the stationary mode. Then it has a meshing option. Obviously this is the geometry where you build the geometry. You can add materials, you can define, you can make some definition before itself, but as of now we don't want to do all those things. Only we want to make a simple stationary. And typically the length in units is shown in meters. We can change it to micrometers if your device is in a micro device, so we typically change it to micrometers. As you can see here, you can see this, you can change it to micrometer because the device is a micrometer device. Then once we select that, is it very small, not visible, but I don't think I have the zoom facility. We have the zoom facility in this. No, right. Anyhow, so try to bear with me. I don't think I have a zoom over here. Selected an option, but zoom is not there. We don't have a zoom facility. Anyhow, so you can see this. I'll try to just mark it. So this is where you are selecting the micrometers, right? So this is where you are selecting such that I can highlight the things, right? So this is the micrometer. So we select from meters to micrometers, right? So once the micrometer is selected, we want to build the structure, a cantilever structure. So to that we select the geometry. You can see here the geometry part. So we select the geometry part, right click on that, you'll get all these options. So we select what do we want to build, a block, a cone, you want to build a block, you want to build a cone, or you want to build a cylinder, whatever shape. So typically we are selecting a block. We're selecting a block to build this. So once you select the block, you can see it appears over here. And once you select this block, typically it's a solid block, it's a three-dimensional block with and we can give the parameters over here. These are pre-filled parameters. We have only taken the final pre-filled version, but you can fill, you can see the dimensions appear in micrometer, and we can pre-fill these parameters with width, depth, and height. So these parameters will whatever dimension. So this is a typical cantilever what we want to make with a length of 200. Even though it is given as width over here, typically it's the length what we are talking. Width is nothing but the length we are what we are talking about. It's a length of 200 meters, then it's a width of 80 meters and height of or a thickness of 20 micrometers. So all the dimensions are in micrometer range, and it is a solid body. As you can see, it is a solid body, a typical cantilever. Then after building the structure, we want to add material to it. So what is the material this cantilever is made up of? So obviously we'll add a component. You can select the materials over here. You can see it is there here on the right side. You have either you can go for recent materials if it is already added, or you don't have, you can go to the MEMS materials. There's a MEMS icon you can see here. Right, highlight it. You can see this is the MEMS icon. So you can go to that MEMS module, and over that you will have the option of selecting the materials like this. So these are all already added from that module. So once you add, they will come into the recent. So you have polycrystalline silicon or silicon nitride or crystalline silicon, gold, even air. Air is considered to be a element over here because if you want to make some parallel plate capacitors, obviously air can be used as a dielectric medium. So obviously air is also a medium to be added. So in this way, we add that component, a silicon to our cantilever. So as soon as we add, you see the color changes. The color changes to blue color. That is with respect to the type of material that you are adding. It attains some different colors. Obviously, when you are adding two different materials, it will show you two different colors to differentiate the materials what we have selected. So once that is done, once the material is added, the next stage is adding physics to it. So we have to coming to the left side. You look at the left side of the screen. We right click on solid mechanics. So when you right click on solid mechanics, you will get a pop-up window like this: free and boundary load, fixed constraint. So obviously, our motto is that we want to fix the cantilever from one end and load it on the other end. Something like our swimming. If you go to a swimming pool, you have a diving board. So people on one end it is fixed, and people move on to the dead end of that beam, the diving board, and from there they jump. So when they jump, what happens? We all know it oscillates. It oscillates as people jump from that board, the diving board. It oscillates. The same is the principle what we are talking in a micro cantilever. But here it is in a micro scale and very much not visible to our naked eye, but you have to look it under the microscope when it is fabricated. So here, all those parameters, that is, we want to fix, make the fixed end, we want to create the loading end and everything. So next step, as I told you, we select the fixed constraint, that is, which end we want to fix. So you can see the XYZ parameter is shown over here of the console. So the XYZ parameter, you can select. You can change the direction also. It is not an issue. We are taking from 0 0 orientation. You can go in the minus x minus y minus z direction also, or you can go anyhow. This is drawn in the positive axis, x y z positive x. So we select the fixed constraint. When we select the fixed constraint, then we have fixed this edge. So obviously, immediately it shows changes the color. You can see. So this edge is 1. When we select, this edge is 1. So every edge is given by a number. It is denoted by a number. So this edge, what we have fixed, is 1. There's a change in color, and obviously the same number will also appear here. So this becomes a fixed end. That is, it is a fixed end. Fixed constraint is nothing but a fixed end what we are talking about. Then we want to do the loading. We want to apply a boundary load. Similar way, if you see over here, there's a boundary load option. After above fixed constraint, there's a boundary load option. So again, we right click on this thing, the same solid mechanics, and select that boundary load and select the surface, the top surface of the cantilever. So we can see this has a number 4. This has a number 4. So this 4 is now loaded. So what it is loaded with, we want to load it with some force. So there's a force defined over here. You can see user defined force, FA. Load defined as force per unit area. Typically, it's something like pressure, or we want to create some stress into this cantilever. So that is what is the force per unit area, the pressure we are trying to apply on the surface of this cantilever. So we are calling it a boundary load. You also have point load. You want to apply only load in a particular point, you can apply. So that varies. So we can select what type of load and through the option. So now, if you see, once the boundary load is selected, I have applied, or we have applied a boundary load in the minus z direction. The minus z direction. That's why we have applied minus 10. We're applying minus 10. Minus, obviously, we all know that force, we don't have a negative unit for force, but here this minus 10 indicates that we are applying the force in the minus z direction. That is from top to bottom. From top to bottom, right? So that's what is the boundary condition, and you can see it's newtons per meter square. Now, once it is the parameters, all the parameters are applied, we have to analyze. So this is where the actual engineering aspects coming to role. So if you see, most of them are aware of signal processing, because whether they're computer science or electronics or electrical people, most of them study the subject signals and systems, and most of them even have the course digital signal processing. So when we do this signal processing, we try to sample a signal. We try to sample a signal or make it into parts to analyze that signal, or we want to make it into samples to what do you say process that signal. So obviously that sampling rate defines the type of processing, the sampling rate defines the end output, the sampling rate defines the different properties of the signal. Similarly, when we want to analyze solid structures, they also have to be sampled, and that sampling process over here is called as meshing. So if you see, there's an option called mesh. There's an option called mesh. So when we select this mesh, it will sample that block into meshes or small blocks. It is nothing but it is making them into blocks again, multiple blocks. So what is the purpose of all these blocks? The purpose of all these blocks is we want to analyze each block, or we have done sampling and we want to do it in parts. So here we can have different levels of sampling. If you see the element size over here, you can see the mesh settings. The pointer, you can see the mesh settings where you have the element size is normal. So if you select this down arrow, you will have fine, extra fine, different options where you can increase the sampling rate or decrease the sampling rate, both. So here the difficulty with this software or any FEM software is that FEM softwares are the ones which are used for finite element modeling. So for any FEM software is that as the size of the device is reducing, that is the dimensions, if any one dimension is reducing, there arises a convergence issue. So here we have taken only some 20 micrometer thickness. Imagine it is 20 nanometer. So as of now, typically, to the knowledge, to the extent of knowledge what I have, we cannot simulate most of the nano technology devices, that is nano layers, because when the size of this layer or the thickness reduces or it reaches into the nanometer range, there arises a convergence issue with most of the softwares, because the only reason is that the complexity of computations increases, and when the complexity of computations increases, the processors that are available are not able to compute those things, and finally they end up with convergence issue, or they give a error called convergence failure. So this is where most of the simulations fail, or most of the people who are working with the softwares fail, because I get plenty of queries. Sir, this simulation is not running. Sir, I have done everything right, everything is same as what is told in the demo class, but still it is not running. So this is where the major issue arises, that is your convergence issue comes because of the sampling process or the meshing process what we are doing. So it cannot be done to the least dimensions as indicated in the early slides. That is up to 0.1 nanometers. But for MEMS, we can use the micrometer range. It can be very much used at, right. So after the meshing process, we have to go to the study. That is, we have to analyze whatever our thought process is, or whatever we want to do. We want to analyze this thing. So we have to do the meshing process. For that, select study, select study. In that, obviously stationary is there, so we select that stationary. So when you select that stationary and run, you have an option here, compute. Study, stationary selected in your compute. If you click this compute, it will generate a output like this. This is the output. You can see the bending state of a cantilever, because the force is applied like this in this direction. Force is applied. Take the annotator. Right. A force is applied in this direction. When the force is applied in this direction, it tries to move downwards. So here, this bending is directly proportional to the amount of force that is applied. So obviously, if some body is some microorganism or some virus element is falling onto this thing, there's a deflection that is happening, and this deflection is directly proportional to the mass that is deposited on this. So we can, if we want to use a direct measurement, we can use a piezo-resistive cantilever, where this bending will generate a stress into the cantilever. You can see the change in colors. This is what is the stress introduced into the cantilevers. So this change in the color, this stress in turn will be converted into resistance. That is what is the piezo-resistive property. And that is what is the transduction process, what we were talking about early in the early slides. So in this way, we will be able to measure the mass, or what is deposited onto this thing, what is the amount of mass that is deposited onto this thing, right? So we can do further analysis. We can do the plots. We can draw some graphs using these things. So at this stage, I will not go into all those details, but still we can do the stress analysis. We can do the what is the amount of we can measure the change in resistance. We can measure the change in capacitance also, if it is for a capacitor, and so on. So, as we started off for designing a gas sensor, the major part in a gas sensor is a heater, a micro heater. Okay. So, for any gas sensing system, a micro heater plays a very important, because we want the compound to be in a volatile state. And of course, our project is also a design of a micro cantilever for determining volatile organic compounds. So everyone might have heard about the styrene accident, or the LG polymers accident, which happened in Vizag, where there was a huge disaster because of these volatile organic compounds only. Styrene is one of the volatile organic compounds. So obviously, determining those things plays a very important role. So we are trying to design a sensor which can be used with more sensitivity in determining this volatile organic compounds. Not only styrene, but all the ethyl, methyl group of compounds. If you take the spirit, the alcohol, or the sprays, even the paints, all these fall under the volatile organic compounds. So a regular exposure to those things will surely damage the human health. That's why if you see the painters, they use mask while painting, because a regular exposure to that paint smell will surely damage the human health. That is very much having the styrene compound in it. All the paints also have the styrene compound in it, but the ratio that they are having is much lesser than what had happened in Isaac in the LG polymers. So if you see over here, this is a typical structure. I have shown you a typical structure of a gas sensor. This is a Mender structure, what do you call it as, or this is a form structure, where it is very much like our heater, the heater what we use for boiling water, very much like that heater, but it is in a micro size. It is in a micro size. So all the things what we have done to do a cantilever design are the same, but here additionally we are selecting a joule heating and thermal expansion process, because the heating process that is occurring. So when you are passing current through these things, when you are passing current through these wires or this structure, obviously there is some temperature generated, and there is a thermal expansion process that is going on. So that has to be monitored, because if it exceeds that range, or we have to know the limits, what is the minimum temperature, what is the maximum temperature, how much amount of current that can be transmitted through it. So if we give more current, it can damage the heater, so the whole process fails. So obviously here joule heating and thermal expansion is one such thing, or one thing that tells about the thing, right? So here, obviously, we select the material. Everything is the structure that is built very much similar to the. This is also done by one of my students. So this is the structure that is built for a micro heater, and you can see after simulation producing uh, a result. Okay, and I didn't give you all those things. So we can build such structures very easily and simulate and produce our own sensors or design our own sensors. So finally, once you are able to design the sensor using a software and correlate the theoretical and simulation results, then we can go for the fabrication process. And as I told you, fabrication process is not the same for every sensor. If you take a cantilever sensor, a optical cantilever will have one fabrication process. A piezoresistive cantilever will have a different fabrication process. A piezoelectric transducer will have a cantilever will have a different fabrication process. So obviously, that is where the actual difficulty arises, and that is where the major issue is there with the research in the NEMS field, the fabrication of the devices. As of now, we have a facility with IIT Bombay and IISc Bangalore under INVP for fabricating devices, but even that is stopped for the past few months because of no funding from the government. And we as an individual, it is very difficult for us to get the devices fabricated at the micro scale. Even I was asking for a quote for fabricating our micro cantilever from IIT Bombay. So Nitin Kale is a friend of mine. I asked him, he told we will charge 15 lakhs for fabricating one cantilever. I was very much shocked. What, 15 lakhs, sir? My budget is only 1 lakh, sir. I have a project of 40 lakhs. Out of that, I can allocate only 1 lakh. He told, no, no, it is not possible. So that is the range of what do you say, or the cost of making these sensors. It is really a huge process or a very costly process. So I spoke to with another friend. I spoke to Germany people. They told that they can do it for 5 lakhs. So another quote I got, and that too for 5 lakhs. So if you see, that is the real difficulty where we arise. So realization of this product or the end product of these devices or the sensors is what is the difficulty with our place. So if you see the parameters that are considered, is typically considered useful for, yeah, somebody was asking me a question. Raise their hand. Screen not able to see, kindly zoom it. Sorry, how do I zoom this thing? Do we have a facility of zooming? Screen, right screen.
Sir, it is visible, sir, clearly. You can
Okay, but somebody was telling it's. I mean, might be in a mobile screen it will be difficult to view, but on a laptop screen it should be okay. Any
Okay, that's fine.
10-inch screen, right? Right. So these are some of the parameters for considered for designing a micro heater as listed. The materials used, the uniform temperature distribution of the heater, mechanical stability and long life, micro heater geometries. So we can optimize these parameters to produce a good micro heater for a specific application or the application whatever we are selecting. Then I will not touch much of this thing because even most of them will not have an knowledge of this thing. Let me make a poll for this thing also. How many of you are aware of the suit? Just I have a question. How many of you are aware of IntelliSuite? Give me 1 minute. I'll have some water.
Sir, how much time is there, sir, still? I'm Tejo Murthy, sir. Rajesh Kumar, sir.
Sorry, is taking
Hello?
water, please.
Okay. Still, can we continue for K. Lakshman, sir? Can we continue for half an hour?
No, no, no. You have to ask the Rajesh sir.
Yes, sir,
How much time
definitely.
will it
But if we want, we can
Okay,
request
okay.
our to close.
Okay, okay. Talk is going well. You can continue.
Right, right. Okay.
As far as me is concerned, it can be continued.
Right, right.
Sir. So how much time I am left with, sir? Tejamut, sir.
No, sir, as you wish, sir, because all participants are interested. But now it is 7:19, so depends on maybe 15 to
Okay,
20 minutes.
another 20 minutes. I'll try to do it fastly.
Right, sir.
Right,
Thank you.
folks.
Okay, right, sir. Go ahead, sir.
I have seen that very few people are aware of IntelliSuite, but this is a software what we have and purchased. And the beauty of this software is that it starts from bottom to top. And in the beginning, I told you we can have a top to bottom or a bottom to top approach. So this software console has a top to down approach, whereas this thing IntelliSuite has a bottom to top approach. That is, we start with the fabrication process. That is, we want to select what are the materials. There's a IntelliFab facility available where we want to select. And also, one beautiful, we don't have any pirated softwares. You don't get any pirated softwares of IntelliSuite or Convener. That's the beauty of this software. So it has a fab facility where we select the fabrication process. I'll just push up these things because most of them will not be able to utilize it anywhere unless until you have a licensed version of this thing. These are the steps. You see, it totally starts with fabrication. We select a substrate, then we do the deposition process. We do using chemical vapor deposition. Then we have the what do you say, spin coating or deposition of photoresist for development and lithography. Then the etching process. So here the total process, whatever we are done, is the fabrication process. That is the simulation. Typically, COMSOL doesn't have this facility. It only has a simulation process of the structures and their analysis. But IntelliSuite can also simulate the fabrication process also, how we want to fabricate or what are the steps that are involved in fabricate. As I told you, every device has a different fabrication process. So obviously, that is the beauty of the software, and we can utilize. We can start with that process, and also we define our parameters, whatever structural parameters we want to design. All of them are defined, and this is a typical U-shaped cantilever designed by one of my students, and the same process. It's a different process. Is different parameter applying, and that is also different. But it is only a what do you say, a stationary process being done or a deflection measurement that is being done over here. So I'll try to move fastly through this thing. How these NEMS cantilevers have become so popular. There are some hundreds of people who have done their research in the NEMS cantilever, and still there is a lot of research going on in this area. So you can see these are the structures, even residents also from where these are the typical structures. When a cantilever is loaded, how they deflect. So this is the thing. This what is my research part where during my research I happened to find the mass of a E. coli cell, Escherichia coli cell. I hope everybody is aware of this Escherichia coli. It is available. It is a bacteria that is available in every water. Whatever water is available, even in the drinking water, even in the purest of the drinking water, what we take from RO water, even that has this E. coli cells. But typically, they are in colonies somewhere. Image, colony of E. coli. Here typically these E. coli are something like this. They'll be in colonies, and these colonies are to some extent, as per WHO, they will not affect our human system. But when that colonies are larger in size, obviously it will affect our small intestine and large intestine, and that is where the problem arises. So as of now, this E. coli cell is of a picogram size, picogram weight. It is in having dimensions in picometers only. In picometers or in nanometers, and we happen to design a cantilever to measure the mass of this E. coli. So if you see, we were talking about that resonant condition earlier. I have used in research. We have a natural frequency like this. So when it is loaded with the cell, there is a shift. It will be always to the left side. The shift will always be to the left side only, because the loaded frequency or the unnatural frequency will always be less than the natural frequency. So there's a change in the frequency, the resonating frequency. So this difference, the change in the frequency, that is, let me use the marker. So from here to here, this is what is the shift we are talking about. From here to here, this is the shift we are talking about. So if you see here, this is the frequency in megahertz. So typically this is around some 1.08, 1.1, some 1.093 megahertz, and the shift is around some 1.07 megahertz. So the change or the shift in the frequency is 1.9 minus 1.7, 1.09 minus 1.0. This is the shift word, and this shift in the frequency is directly proportional to the mass of the body. So that's what the prime mode. So this is the most sensitive process of measuring the mass of microorganisms, and with respect to the mass of the microorganisms, we can determine what kind of microorganism is that. Even for virus also, we can use this. So these are the different things. So obviously we cannot do it for one single cell, so we do it for multiple cells, 800 cells. So you can see how it varies for number of cells, because they always appear in colonies. So we can observe these E. coli cells under microscope. If you have 100x zoom microscope, you can take a droplet of water on a slide, and under the microscope you can observe these E. coli cells. Then typically this is a optical cantilever. As I told you, it uses the optical property, that is a laser beam is projected, and the resonant frequency is measured with respect to the light property. So it needs a huge setup for measuring that change in resonant frequency. Then always measurement in cantilevers can be done with two variations: response with respect to change in stress, with respect to change in mass. Okay, so I'll not go into all those details. Typically, a cantilever can be operated only in two modes: static mode and dynamic mode. But there's one mode, additional mode, heating mode. Generally, we are all aware of bimetallic strips, the one which is used, principle which is used in refrigerators or VC machines, where once the temperature, as the temperature is changing, one metal will have a larger thermal coefficient of expansion, the other will have a lesser thermal coefficient of expansion. So when the temperature is changing, one will expand more, the other will expand more. So obviously, it will lose contact with the power supply and it will stop. The cooling process in the refrigerator or the AC machine will stop. Again, when it's the temperature will be increasing, slowly it will contract, and again it will come in contact with the power supply, and again it will restart. So that is the automation process that is used. But this is less used in a micro scale. Most of the applications that we find in the micro cantilevers are with a static mode and dynamic mode only. So we generally we can ignore this heating. So in the static mode, the surface stress plays a very important role. What is the stress that is induced into the cantilever? To what extent, and this stress is converted into either piezo resistance, more very commonly used principle. That is where we can generate a handheld devices is a piezo resistive principle or a piezo resistive transduction process where we can use it. Then coming to dynamic mode, as I told you, it is a resonating condition that is used. So obviously, we are trying to measure that resonance shift in the dynamic. So as I told you, it is used for virus detection. There are different kinds of viruses available. So it is also used for virus detection. You can see this is from per where it was used for detecting mass of a single virus particle. So virus means to say any kind of virus can be determined using these cantilevers. And I mean, if you want to know what are the properties of this virus, obviously first you should know, or you have to separate that virus and you have to extract it and do. So people have worked on the pandemic that is going on, the corona COVID-19 virus, and they are still in the process of extracting what the actual properties of this COVID-19 virus is. It has some similarities with the SARS virus, which was there earlier, but still there are some things beyond that. So people are still researching. So once the actual properties of the virus come out and they are able to know the total details of the virus, then what do you say, the vaccination process will obviously become easier. So that is where the actual difficulty arises. As we all know, as researchers, finding getting a research problem is will be a major issue than finding the solution to the problem. So most of the people who are in the research field, they'll be spending years together to find out a problem statement. Then once they get the problem statement, we can shoot. We will have multiple solutions for that, and people will work. So that's what is the issue with the virus also. Determining the properties of the virus is always a major issue, and cantilevers are very much useful. The micro cantilevers are very much useful in doing these things. Right. So this is a single cantilever, just for your knowledge. Gold dot. You can skip all these things. Less time. This is the bending property. What I was talking about. Yes, sensors. Right. Yeah. So, if it is okay for you, I'll just briefly try to explain you how we can do some to some extent. You cannot do it to the extent of COMSOL or IntelliSuite, but because most of them are having MATLAB and very much used to MATLAB from years together, and most of the students use the pirated versions of MATLAB. I'll just try to introduce you experimentally, I mean, sorry, through MATLAB, directly through MATLAB rather than slides, how we can use MATLAB for FEM, finite element modeling, up to some extent. So just confirm me if the MATLAB window is visible to you. Let me open. Once I open, I'll. Is my screen visible? Even though I minimize the.
Yes, it is visible, sir. No
Yes,
problem.
yes, it is visible,
Is
sir.
MATLAB visible?
Continuous.
MATLAB.
MATLAB is not visible. Just the
It is opening actually.
presentation slide is there.
Only presentation slide. I've shared the whole screen.
Yes, now it is visible.
Oh, fine. Right. So, let me make a poll again. Sorry, I'm having so many polls because if it was face to face, I would have asked you to raise your hands. But here, I'm using the technology. How many of you are aware of FEM in MATLAB? If it is yes, you can give yes. If it is no, you can give no. I don't know, even my scholars, they should be, how many of them are aware of this? So I'll just introduce you to this come tool in MATLAB. Not go with much details because the time is very less. We'll conclude. Right, good. So most of them are unaware of this thing. Just I'll introduce you. You can use it to some extent. But still, the response is very less. Almost 50% of the people are responding. That's why I'm also displaying the poll results. Okay, so we'll fastly close. So here, as everyone knows how to use MATLAB, I don't know there one or two people who don't know how to use MATLAB. I'm sorry for that. I'll directly push off how to use this tool. So we have the apps tool in MATLAB where we have a PDE modeler. You can see there's a PDE modeler. I'll quickly show up in another 5 minutes. Okay, please bear with it. Too late. Remember, sir.
But
Right.
only 5 minutes, I think. So.
Yeah. So you see, you can. I mean, it's a 2D visual only. As of now, the 3D. I mean, drawings are not available. 2D only. You can draw a structure, or you can define the parameters. You have the options over here. You can see you can draw a square, ellipse, then you can define the boundary conditions, specify the boundary conditions. Okay. We have to select, then we have to give the specifications. What are the specifications, coefficients, okay, and everything. The solving parameters, what solving you want to do. I have not selected anything, just one. Okay. I'm trying to push off. You can just scroll through this thing. Yeah. You can see we can do the structural mechanics, plane stress, plane strain, electrostatic, magnetic, DC, AC analysis, whatever we have seen in COMSOL. Almost similar kinds are also available over here. Okay. So please explore these things. So that if still we have anything, we can discuss in any other session like this. Okay. So please bear it. Yeah, just I will show you the machine part. You can see this is the result part. Sorry, the machine part. Yeah, you can do the mesh. See, mesh is also done very much similar like that. And this is the solving part. We can have the solving for a 3D plot. Solving is can be done in 3D plot. You'll get a 3D plot. Okay. So all these things you can study and do it. So or still we have a help facility. Everyone is aware of MATLAB help. You can go over there. The MATLAB help. You can go to examples. There are a good number of examples also given over there. Even our cantilever example is given over there. You can go to the PDE, partial differential equation toolbox. This is the PDE toolbox. You can see over here the examples. This is deflection of a piezoelectric actuator, dynamics of a damped cantilever beam, everything. The script is given already with examples for a damped conditions, clamped conditions, okay, with a whole deflection analysis with a bracket. So just you can you do it, and this is available. This toolbox is available from 2018 version on. It is not available in the older version, right? So that's it. What else we have to conclude? Because time is up. Yeah, right. So we'll conclude with a recap and conclusion. We introduced the role of sensors and IoT, NEMS sensors, and design of sensors using tools like console. Then, obviously, as I told you, NEMS design is interdisciplinary course. So this is the lab facility what you have, and these are my scholars who have been helpful in picking out all these things. They helped me in making the PPT also. My scholars Suresh, Ashwin, Ranjit, and Srikanth. And these are the facilities what we have. Anybody interested can use these facilities also. Thank you for your patience and interest. So I would like to thank the HOD, P. Venkateswara Rao, and of course my dear friend P.H.S. Tejo, and of course the CR Reddy management for giving me this opportunity. Thank you. Thank you, one and all.
Rajesh garu, thank you.
Sir, చెప్పండి sir.
Thank you very much, sir. This is Dr. Tejo Murthy. Thank you very much for nice presentation and the practical presentation also. We liked it very much, but because of this time is going on, so I request one more presentation in future also. And
Sure.
now floor is open for anybody to ask some questions. Please, 5 minutes, please bear. And any interactions are there? Somebody have responded through chatting, and now the floor is open for questions. Anybody, please. So
Any
if
questions?
no questions are there,
There's a participation form and quiz. I think Tejo will share with you. It's only for to know how many of you, have got an introduction to the things. I don't want you people to learn everything over here, but at least you should get introduced to the things, and hope this should be useful for you people to mold your research into the MEMS. As I told you, MEMS is not something different from VLSI. That is where actually Murthy sir and we used to work together, and we are still working together. But still, you can mold yourself. Thank you.
so thank you very much, sir, for this nice presentation, and we are receiving very good feedback through the chatting also. You see, so many are responding very well. And now
Yes, sir.
I request our HOD sir for closing remarks. Sir, over to you, sir. HOD sir.
Thank you, Rajesh garu. Nice presentation.
Thank you very much, sir.
Sir, after this COVID-19, we are inviting you to a personal visit to our department, sir.
Sure, sir. Sure. Thank you.
Thank you, thank you. Over to
Thank you.
Tejo Murthy garu, please close the session.
Sir, thank you very much, sir. And
Tejamurthy garu, 1 minute. Tejamurthy garu.
right. Continue.
This
Continue,
is
sir.
Lakshmi Narayana, sir, faculty in EC department, sir, CR Engineering College.
Sir,
Thank you very much, sir. Dr. Rajesh Kumar, sir. This is Lakshmi Narayana from EC department.
Oh, thank you, sir. Thank you.
The things you are depicted and the illustration of the slides complete. The talk is very excellent, sir.
Thank you. Thank you very much, sir.
Once again, thank you very much.
Thank you, sir.
For this
For the
nice talk,
answer.
sir. Thank you. Thank you, sir.
So now it is time for conclusion, because already time is over, and I am requesting Dr. Rajesh Kumar garu to be in touch with us in future also. Most of our scholars are doing in MEMS, and he is cooperating with us, and I request him to continue in future also. Thank you very much, sir.
Thank you, sir. Thank you all. So we'll end the meeting.
Okay. Right, sir. Thank you.
Thank you, sir.
Thank you for all participants. You have actively participated, and we are requesting tomorrow also there is a session on NEMS fabrication process by Nitin Kali sir from IIT Mumbai. Thank
సార్
you, sir. Thank you very much. Now,
ఆ లింక్ షేర్ చేయండి సార్ అందరికి చాట్ బాక్స్ లో షేర్ చేయండి
right, sir.
చాట్
Right,
బాక్స్
sir. Right.
చాట్ బాక్స్ లో షేర్ చేస్తే అందరూ లింక్ చేస్తారు
కాదు సార్, వాట్సాప్ లింక్ ఉంది మాకు, దాంట్లో పెట్టేస్తాం.
అందులో పెట్టి ఓకే
Right.
థ్యాంక్ యూ వెరీ
Thank you very much, sir. Tomorrow we'll meet, and we are waiting for the Nitin Kali sir session also. Thank you very much.
థ్యాంక్ యూ సార్
Bye.
Now I am ending the meeting.
Okay, now everybody can leave the meeting.
కదా